Welcome to the Deep Dive, where we break down complex research and give you the essential architecture for understanding it. Today, we're getting into a really pivotal new paper, one that I think fundamentally redefines how we should be thinking about sparsity and scaling in large language models. For a while now, the main blueprint for scaling has been, the mixture of experts paradigm, MOE.
Right. It gives us conditional computation.
Exactly. It's a way to scale up capacity by only activating some parameters based on the input. That's been the go-to scaling mob. But the real insight in the paper we're looking at today is that the transformer architecture, it just doesn't have a native tool for a totally different task.
Which is knowledge lookup.
Knowledge lookup.
Yeah, it's really an issue of how you're allocating your computational budget. Language modeling has these two really distinct demands. On one hand, you have complex compositional reasoning.
Right, which needs that deep dynamic compute that MOE is great for.
Exactly. But then you have this other thing, knowledge retrieval. Just handling static, local, highly stereotyped information. Think named entities, dates, patterns you see over and over. And the way we do it now is it's incredibly wasteful. LLMs are basically simulating these simple static lookups using really deep, really costly dynamic computation.
So it's like using a supercomputer to do basic arithmetic.
Precisely. Think about resolving a name like Diana, Princess of Wales. That can take up multiple early layers of attention and feed-forward networks. The model is burning through its sequential depth just to reconstruct something that should be an instant lookup.
And that's the gap this paper is trying to fill.
That's the optimization gap.
And their solution is actually quite elegant. They introduce what they call conditional memory as this new complementary axis of sparsity. The actual module that does this is called Engram.
And at its core, it's basically a heavily modernized, very specific Engram embedding system. The whole thing is engineered for constant time, O1, deterministic lookup.
So that duality is really the core idea we need to focus on today. We're moving beyond just conditional compute with MOE.
To also embrace conditional memory with Engram, making it a first-class citizen in the architecture.
Exactly. So our mission for this deep dive is to really break down Engram's architecture, look at the scaling laws that tell you how to balance it with MOE, and then analyze the performance gains, which are surprisingly broad.
And we'll touch on the system-level advantages, which are a huge part of the story.
Okay, so let's unpack the architecture. The paper sets up this really clear conceptual split. You have compositional reasoning, which is dynamic and handled by MOE.
And then you have knowledge retrieval, which is local, static, stereotyped. And that's now Engram's job. It's a structural separation of, storage from computation.
So how does it actually fit into the transformer backbone?
It augments it in two phases, retrieval and then fusion. And the key thing is it's not at every layer. It's placed very strategically at specific layers to intentionally decouple that memory processing from the main attention and FFN blocks.
Let's start with phase one then. Sparse retrieval, using hashed engrams. I saw they do something first, though. A tokenizer compression step. Why is that so critical?
It's critical because standard subword tokenizers they can fragment meaning. For instance, Apple with a capital A might get one token ID, but Apple with a space before it gets a totally different one.
So for lookups, that's a nightmare.
It's a nightmare. If you want to efficiently look up a fact about Apple Inc., you need consistency. So they project the raw token IDs into these canonical identifiers. They use things like NFKC normalization and just simple lowercasing.
And the result is pretty significant, right?
Oh, yeah. They report a 23% reduction in the effective vocabulary size for a 128K tokenizer. That directly makes the memory table much more efficient.
Okay, so that's a smart pre-processing step. It cleans up the input. But then you have the massive combinatorial problem of engrams. How do they make that manageable and still get that O1 lookup?
Through what they call multi-head hashing. They manage the combinatorial explosion with a deterministic function, let's call it phi, that maps the compressed engram to a very specific index in this huge embedding table.
And the O1 time comes from it being a direct hash, not a search.
Exactly. No complex search, no attention over the memory. It's a direct deterministic operation. And to handle the inevitable hash collisions, they use K distinct hash heads for each engram order.
To increase the retrieval capacity.
Right. And then the retrieved embeddings from all these heads are just concatenated together to form the final memory vector.
Okay, so that gives us a static memory vector. Let's call it ADET. But that's not enough. Memory without context is, well, it's useless.
Right. It doesn't know if Apple is the company or the fruit.
So that brings us to phase two, context-aware gating. How do they make these static priors aware of the sentence they're in?
This is where the model's dynamic state comes into play. The current hidden state, HT, which has all the global context from the previous layers, acts as a dynamic query. And they project that static memory vector, etet, into keys and values. The real magic is in this little scalar gate they call alpha.
Walk us through that gate calculation. That seems to be the core of the alignment mechanism.
It is. The scalar gate, alpha, is calculated by taking the RMS norm of the current hidden state and the retrieved key, and then just passing it through a sigmoid. Functionally, you can think of it as a dynamic confidence score.
So if the context and the memory don't align,
If the model's current context, HT, strongly disagrees with the static memory key, maybe because of a hash collision or just polysemy, that alignment score is low. A low alpha value suppresses the memory, driving the gate towards 0. It ensures only relevant memory gets fused into the forward pass.
and I saw they add a small convolution right before the final integration. What's that for?
That's right. It's a short, depth-wise causal convolution. It does two things. First, it expands the local receptive field just a little bit beyond the strict engram boundary. And second, it adds a tiny bit of nonlinearity to refine those gated values before the final residual connection.
Makes sense. Let's talk implementation for a second. Integrating this with a big multi-branch backbone like MHC with 4 branches. That sounds like it could get complicated. Do they just quadruple the memory table?
No, and that's where they're clever. They use a parameter sharing strategy. The huge sparse embedding table is shared. The value projection, WV, it's also shared across all branches.
But not the key projections.
But they keep M distinct key projections, one for each branch. So they're sharing the memory content, but keeping the how it's filtered separate for each branch. This maintains the expressivity of the gating, but it's also a huge win for the hardware.
How so?
Because you can fuse all those linear projections into a single, dense FP8 matrix multiplication. And that's a major optimization for maximizing GPU utilization.
Right. Okay, so that's the architecture. Now let's shift to the quantitative side. You have 2 different sparse primitives, MoE and Engram. How do you figure out the optimal way to divide your resources between them?
So they formulate this as a sparsity allocation problem. The main constraint is that both the total parameters, ptot, and the activated parameters per token, packed, are held fixed.
So the model size and the cost per token are constant.
Exactly. The variable is the inactive or sparse parameter budget. And the key metric they define is this allocation ratio, rho, which is just the fraction of that sparse budget that you give to the MoE experts. The rest goes to Engram.
And the result of this experiment is, I think, the most convincing piece of evidence in the whole paper, the U-shaped scaling law. Tell us why that U-shape is so important.
The U-shape is so important because it shows that neither extreme is optimal. It was consistent across both of the compute budgets they tested. If you set rho to 100%, so a pure MoE model,
Performance is suboptimal.
it's suboptimal. You're forcing this deep, expensive network to simulate a simple knowledge lookup table. But on the other hand, if you go too far the other way, you also lose performance. The sweet spot, the bottom of that U, was consistently found near a rho of about 75 to 80%.
So reallocating just 20 to 25% of your sparse capacity from experts to this deterministic memory gives you the best performance.
It gives you outsized gains. In the 10B model, for example, the validation loss dropped from 1.7248 to 1.710 just from that small shift. It really proves the 2 primitives are complementary. They're good at different things.
They also did another experiment they called infinite memory scaling. What was that about?
Well, since NTM's computation overhead is 0.1, they could just keep making the memory bigger. They scaled the memory budget up to around 13 billion parameters and attached it to a pretty small 3B MoE backbone.
And what did that show?
It showed that Enneagram is this distinct, predictable scaling axis. The validation loss followed a really strict power law, a log linear trend as the memory size went up. This is huge. It validates Enneagram as a knob you can turn to increase capacity without increasing the per token FLOP cost.
Which is not something you can say for adding more experts or making layers wider.
Not at all. That directly increases your pact. This is capacity without the computation cost.
Okay, let's get to the empirical results because this is where things get a little counterintuitive. They compared their Enneagram 27B model against a standard MoE 27B baseline, both strictly isoparameter and iso-FLOPs.
Right. And as you'd expect, there were gains in knowledge-heavy tasks. MMLU was up by 3 points, CMMLU by 4. That makes sense?
But that's not the surprising part.
Not at all. The largest improvements were in generalized complex reasoning. Big Bench Hard went up by 5 points. ARC challenged by 3.7. Even coding and math, like human eval and math, saw significant bumps.
Hold on. Why would externalizing static knowledge make a model better at dynamic, hard reasoning puzzles? That feels completely backwards.
It does, but that's the whole point of their mechanistic analysis. They confirm this idea of effective deepening. The hypothesis is that by offloading all that early layer static reconstruction to Engram, you free up those layers to start working on the high-level compositional reasoning much, much sooner.
So you're essentially getting more functional depth out of the same number of layers. How did they prove that?
They used a couple of techniques. First was logit lens analysis. They showed that the Engram models had a systematically smaller KL divergence in the early layers compared to the Murtagh baseline.
Meaning they get to a good prediction faster.
Much faster. The model reaches a prediction-ready state much earlier. It's skipping the whole cognitive burden of memorization.
And the other piece of evidence was centered kernel alignment, CKA.
Correct. The CKA heat maps, which measure how similar the representations are between layers, showed this really distinct upward shift from the diagonal. This meant that, for example, Engram's layer 5 was functionally behaving like Moe's layer 12.
Wow. So that's the smoking gun.
That's the smoking gun.
Yeah.
By handling the knowledge lookups, an Engram functionally gives the model several extra layers of compositional depth, but without adding any of the compute.
And just to close the loop on the mechanism, the visualizations of that gating, that context-aware piece, it works as advertised.
Absolutely. The visualizations of the alpha gate show it activating very strongly, specifically when static patterns in named entities are completed. It works for English phrases like Milky Way, and for complex Chinese entities like chess, the 4 great inventions. The mechanism correctly identifies and fuses the knowledge only when the context is right.
Okay, the final piece we need to cover is system efficiency. This is maybe the most practical contribution, the deterministic nature of the lookups. Why is that such a game changer for the infrastructure?
It's huge because Moe routing is dynamic and unpredictable. But Engram's indices are deterministic. They depend only on the input sequence.
Which means you know what you need before you need it.
Exactly. And that enables this prefetch and overlap strategy during inference. Since the system knows all the memory indices it's going to need ahead of time, it can start asynchronously prefetching those embeddings from cheap and abundant host memory over PCIe.
And you hide that latency by doing it while the previous transformer blocks are crunching away.
You completely mask the communication latency with computation.
That sounds great in theory. Did the empirical numbers back it up? Can you really offload, hundreds of billions of parameters to slower DRAM without a major performance hit?
The overhead was minimal. They tested offloading a massive 100 billion parameter embedding table entirely to host DRAM. The penalty peaked at only 2.8% overhead on their 8B backbone. It's a fantastic validation of that communication computation overlap.
And it fundamentally challenges the idea that all your model parameters have to live in that expensive, scarce, high bandwidth memory on the GPU.
It really does.
So let's connect this back to the big challenge in LLMs right now. Long context. How does Engram help with that specifically?
Well, by delegating all those local stereotype dependencies, the stuff that attention often wastes its time onto these O1 lookups, you just free up the transformer's attention capacity.
And that freed up capacity can then focus on the hard stuff.
It can focus on the truly global dependencies, the complex relationships that span thousands of tokens in a long context window.
They showed this with something they called an isoloss setting, right? Which sounds like a very rigorous way to compare the architectures.
Exactly. It's a way to isolate the architectural effect from just, training longer. They compared the Engram 27B model after 46,000 steps to the Moe baseline at 50,000 steps, which is when they had the same training loss.
So an apples-to-apples architectural comparison.
A true apples-to-apples comparison. And in that setting, Engram just blew the baseline away on high-context retrieval and reasoning tasks. On multi-query NIAH, it scored 97.0 versus 84.2. On variable tracking, 87.2 versus 77.0. It's clear proof that this separation of concerns leads to a better model when context really matters. So at the end of the day, the core thesis really holds up. Engram successfully establishes conditional memory as this indispensable first-class modeling primitive. It perfectly complements conditional computation for Moe.
And it solves that deep network inefficiency of forcing dynamic compute to simulate static lookups. So the key takeaways for you, our expert listener, are really the 3 pillars of this paper. First, the quantitative guidance you get from that U-shaped scaling law.
Second, the surprising performance boost in reasoning, which is driven by this functional equivalence to having a deeper network.
And third, the system-level breakthrough of having almost no inference overhead because of the deterministic addressing.
And that all leads to the final provocative thought. The success of Engram really hinges on this physical decoupling of parameters, the memory, from FLOPs, the computation.
Right.
So if you accept that this memory module can scale up to 100 billion, maybe even more parameters, and it can live in host memory with almost no overhead, the entire landscape of model design changes.
So the question becomes,
The question becomes, how does this shift force us to redefine the fundamental balance between PTOT, the total size of your model, and PAC, the actual computational cost per token, when we design the next generation of these ultra-sparse models? That's the new horizon this work opens up.